Hi, everybody. Thanks for having me today at Enterprise GraphQL Conf. Really excited to be here to talk to you about how GraphQL has evolved over the last year at Airbnb. My name is Adam, and I work on API infrastructure at Airbnb. Today, I'm going to talk a bit about a project called Viaduct that my colleague Arun and I, pictured here, as well as many others, have been working on for the last year. Viaduct aims to unify Airbnb's microservices within a unified graph. So let's dive in and talk more about that. Any talk that mentions microservices wouldn't be complete without the obligatory Conway's Law slide. So to remind everybody about Conway's Law states that any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. And I wanted to call this out explicitly because we see this phenomenon again and again in microservice architectures, and certainly it resonates with what we see at Airbnb. Today, like many companies, we have hundreds of microservices in production at Airbnb. They're owned by teams large and small, and just as Conway predicted, map reasonably strongly to our organizational structure. But even though the services themselves might map to our organization, as all of these services start to talk to one another, a call graph emerges that looks maybe a little something like this. Looking at this image, one is reminded a bit of the dreaded spaghetti code that we so often find in legacy systems. Just as spaghetti code becomes hard to modify and understand over time, so does this kind of spaghetti SOA, so to speak. Take the data that powers the user profile page, for example. To access all the data you may need about a user, you may have to call 3 different services, all owned by different teams and without unified APIs. Need data about a reservation? That's scattered among more than 5 services. After all, a reservation needs to pull in user data, listing data, pricing data, etc. As we've moved to microservices, our front-end APIs have also changed. We've moved away from more reusable REST APIs and really embraced the back-end for front-end pattern, building what we call presentation services to power our product surface areas. So instead of API/v1/listings or API/v1/reservations, we're starting to build APIs that are named more after their product surface area, PDP listing details or checkout. Along these same lines, we even went so far as to layer GraphQL on top of these opinionated endpoints, building what we called service-oriented GraphQL, which I've spoken about publicly before. In service-oriented GraphQL, we have our schema namespaced by service name and endpoint. And we've derived this GraphQL API automatically from our thrift services. You'll notice that this API, while it's still GraphQL, is not very graph-like. All of what I just described is us really coalescing around an RPC-based service mesh. This is understandable. After all, this is how most folks do microservices. Build a bunch of services, tie them together with Thrift or gRPC, and move on. This type of architecture is an example of procedure-oriented design applied to a distributed system. We're all familiar with procedural-oriented design. It's a pattern that's been around since the beginning of computing. The earliest programming languages were designed around organizing groups of procedures into modules and exposing public APIs from those modules for others to consume. Our observation, however, is that for any internet service, data is really at the core. We came to realize the procedural-oriented approach was getting in the way of truly taming our ever more complex SOA. Let's take a look back to history again. In the late 1970s and early 80s, as the Smalltalk programming language was introduced to wider audiences, object-oriented design started to hit the mainstream. Programs could now be designed around the data they provided and consumed, rather than around simply groups of APIs. This was a key paradigm shift in how we develop software, and as I'm sure we all know, it has become pretty successful and widely adopted. Despite the progression in software design to object-oriented design, our distributed systems architectures often fall back to that procedural approach from days old. Even state-of-the-art service messages bake in assumptions that all services are communicating in a procedural fashion and have no knowledge of the underlying data that those services expose. What if we applied a more data-oriented approach to the design of our distributed system? Rather than a procedure-oriented service mesh, organizing our services strictly around RPC calls and APIs, what if we instead made data a first-class citizen moving from a procedure-oriented service mesh to a data-oriented service mesh. With a procedure-oriented service mesh, developers of a service obtain data by determining which services vend that data that they need, and then directly wire those services to those vendors. With a data-oriented service mesh, however, developers are simply requesting the data that they need, and the service mesh finds the vendors on their behalf. Enter Viaduct. Viaduct is the core building block of Airbnb's take on a data-oriented service mesh. To expand on that more, Viaduct unifies data access internally and through our publicly accessible API, exposes a GraphQL query interface and consolidated schema, and provides a declarative resolution model for hydration and data transformation. Let's dive deeper into each of these pieces of the Viaduct system, starting with how we unify data access. Here's a 30,000-foot view of our service architecture at Airbnb circa 2019. It's diagrammed in a way that looks a bit less spaghetti-ish than that slide I put on the screen earlier. In our architecture, we have data services, derived data services, and presentation services. Data services wrap databases, expose single models. Derived data services kind of fetch data from here or there, combine it together, and perform some business logic. And presentation services put all that data together from all those downstream services in order to provide a usable API to the product. Let's zoom into a typical service and look at what it does. A typical service at Airbnb ends up being made up of four main parts. The first is data fetching and hydration. Take something from service A, something from service B, and then combine those into a single API response. A very large portion of the code in our services is just doing this, and many services are probably writing the same boilerplate to get the same data all over the place. Services are also, of course, responsible for doing data transformations and performing business logic on the data that they fetch. This is pretty much the core of why we have services in the first place. Services perform policy checks to ensure the data that they're vending is being seen by the right user. And finally, some services have a bunch of other types of complex logic within. They orchestrate writes across multiple models, perform complex personalization, do blending, this is especially the case for search, or perform other compute-intensive operations. Viaduct reduces the data fetching and hydration boilerplate that we find throughout our service hierarchy, while also simplifying the simple data transformations and business logic that our services perform. That's what we're trying to get at with Viaduct. So if we go back to our 30,000-foot architecture diagram, let's look at what this is starting to look like in 2020 as we roll out Viaduct more widely. Well, first you can see there are less lines, but you'll notice in this diagram, Viaduct is really surrounding the whole infrastructure. I drew this in 2 dimensions. My Keynote foo is not good enough to make it 3 dimensions, but imagine just in your mind's eye that this were drawn in 3 dimensions. And imagine that Viaduct is sitting as this base layer, forming the mesh between services. It's sitting at the bottom. And then these services are layered on top. The connection between services still exists as it did before, but the difference is that Viaduct acts as this mesh. The services aren't declaring explicit dependencies between themselves in the same way they did in the typical SOA. With Viaduct, the data dependencies are what become explicit. When a service needs user data or listing data or reservation data, they request it from Viaduct, and Viaduct brokers the connections to the services that contain this data. These service dependencies now become implicit and controlled by Viaduct and the data hierarchy. We've changed the organization of our system to be around data rather than services. In some cases, we've been able to remove or combine services or replace them with the programming model that Viaduct provides, which I'll go into more in a minute. You can see that especially with the presentation logic, the purple box here. We've kind of gotten rid of the concept of a presentation service and built that into Viaduct itself. But the goal here isn't specifically removing services or going back to some type of monolithic architecture. Rather, our focus is bringing sanity to our large microservice architecture and making data a key component and binder. So now I want to talk about Viaduct's GraphQL query interface and consolidated schema. This is a GraphQL conference after all, so I'm pretty sure we're all generally familiar with GraphQL. GraphQL is really the backbone of Viaduct. It's the engine that makes it all work. Viaduct uses GraphQL as its query interface and is built on top of the open source GraphQL Java library. On top of GraphQL Java, Viaduct creates high-level abstractions for type resolution, derived fields, and observability that allow us to interact with services in an opinionated and reliable way. Viaduct is primarily called from external clients, for example, the Airbnb.com web and mobile applications, but can also be accessed by internal clients using a JVM GraphQL client for other Java services to use. The schema is really the heart and the soul of Viaduct. It's sacrosanct in a way. Unlike other distributed GraphQL systems like GraphQL modules or Apollo Federation, Viaduct deals with the schema as a single artifact. And we've implemented several primitives that allow us to keep this unified schema while allowing for teams to collaborate on that schema productively, many teams. In Viaduct, the schema is the source of truth. Everything kind of falls out of the schema. The schema is the building block of the data-oriented service mesh. Our schema lives in one single folder in our monorepo, and we collaborate on the schema in its SDL format. Let's look at the excerpt of this consolidated schema that I was mentioning. This is just one node in the schema, the user type. You can see there's lots of custom GraphQL directives here, and that's us trying to make Viaduct very configuration driven. So let's look at what some of these directives actually do. The first one I want to call out is the scope directive. We have this directive because types in this consolidated schema can belong to different schema scopes or different projections of the schema. This allows our single unified schema to power both the main Airbnb API as well as internal APIs for internal tools. Even with a data-oriented service mesh, encapsulation is important. And by building scoped projections of the schema, we are able to continue to enforce that encapsulation for different callers, even though we have this one unified schema. Also, every type in the schema, as well as fields within those types, have teams as owners. This lets us up-level our observability abilities inside of Viaduct. Using this ownership information we baked into the schema, we know who to notify if error rates or latencies increase for a given type or field. Having this information in the schema lets us easily determine statically who owns what. So continuing with the consolidated schema concept, let's talk a bit more about the declarative resolution model for hydration and data transformation in Viaduct. So looking at our schema again, now let's take a closer look at this directive, service back node. We built in this concept of node-based data loading as a key concept of how you add data to the Viaduct platform. Basically, everything in the Viaduct schema is a node or an edge, and we provide the tools in Viaduct to help our service graph conform to this model. So here we're saying that this user type is powered by a service called user block, and that we can fetch information about the user by calling a thrift method on that service called load users. Now, when consumers query the graph for this type, Viaduct knows how to resolve it from the underlying service appropriately. Looking at the ID, first name, and last name fields, we notice there are no special directives that tells Viaduct what to do with these fields. That's because it isn't necessary. Our load users response from our user block service also has fields named ID, first name, and last name. And thus there's no special action required for this data to be queryable through the graph. So to add fields to the graph, presuming there's no special logic involved, you literally just add them. There's no special, there's nothing special involved here. However, one main purpose of this consolidated schema is to be able to unify our data access patterns, and that includes unifying naming conventions. The key directive lets us rename fields from the underlying service response to fields in the schema. Viaduct doesn't stop at letting us expose data from single services. On the contrary, Viaduct's primary goal is to allow us to be able to relate data from services together. Many of us might be familiar with the concept of a GraphQL connection, popularized by Relay in the GraphQL connection spec. In the example you see here, we have an owned listings field meant to represent the Airbnb listings a given user owns. And we can see this is referencing a user-owned listings connection type. Looking at that type, we see another directive that looks very similar to one we've already talked about, service back connection. This directive is very similar to service back node, but it understands how to bridge two types together. These two primitives, service back node and service back connection, do most of the work in letting us tie our services together into a unified data graph without writing any code to do so. We generate resolvers based on all of these schema directives at build time. All of the data fetching is handled for you right out of the box and is purely driven by the definitions you provide in the schema. We make heavy use of the data loader pattern in Viaduct, and thus can make sure our calls to these downstream services are batched optimally. Typically, the data loader pattern, if you're familiar, is applied in such a way that within a given request, there's an in-memory cache that prevents the system from re-requesting data it's already fetched during that request. Remember, though, that Viaduct is a data-oriented service mesh. We can take this data loader pattern further, and instead of just using an in-memory cache, we can use Redis to build an intra-request cache that lets us apply this data loader pattern even when multiple service calls are involved. Here's an example of how that works. So a request comes in with a unique identifier from the client. And we fetch some listing data from the listing service by its ID. That data is returned to Viaduct, and Viaduct stores that in its intra-request cache. Now we go to our other service, it's called co-host, to find co-hosts of a listing and fetch data from it. Within co-host, it needs access to listing data in order to be able to run business logic that's required for actually finding the co-host of the listing. So instead of going down to the listing service and fetching that data itself, it's going to call back to Viaduct, and Viaduct is going to be able to pull that data from its cache without fetching it again from the service. Finally, the co-host service is going to respond back to Viaduct. Viaduct is also going to cache its data, and the request is going to continue. All of this is keyed by that request ID, that unique request ID that we've generated at the beginning of the client request. That's how we can tie all of this together. So one thing you'll notice is that we haven't written any code yet. What happens when we want to do something that isn't just load this thing from this service? What happens if we want to write some business logic? Let's go back to our schema and let's spotlight another field, isHost. Notice how this field has a new directive, derive field, and specifies a class path. This path is pointing to what we call a derived field provider class. Derived field providers give us an opinionated way to derive data from the graph on the fly. So here's the interface for a derived field provider. You can see it's quite simple, and it has two function members, get fragment and resolve. We know that we can get the data for our isHost field from data that already exists in the graph. And in fact, from data that we've already associated with our user type, the data we've just talked about, owned listings. This owned listings field is a connection, and connections return us optimized lookup of the total count of edges for that connection. This is all the data we need to determine if a user is a host. So we can build this GraphQL fragment that represents the data we need and return that from the getFragment function of our derived field provider. When Viaduct executes this field, it will execute this fragment against the graph, just like a normal GraphQL query, and provide that data to the resolve function, the other part of our DFP contract. Now that we have the data we need, we can perform our simple piece of business logic. You can see it's only 3 lines that derives the isHost value. This is just us checking whether the total number of owned listings is greater than 0. That was a very simple derive field. We looked up a single piece of information from the graph and derived a simple value from it with minimal business logic, but we can take this much further. At Airbnb, we've been investing a ton in server-driven UI, allowing our backend to return structured data that instructs frameworks on our web and mobile clients how to render UI. This lets us more quickly evolve our clients, especially our mobile clients that have longer release cycles, without modifying any front-end code. Historically, we've had several ways for backends to provide this structured data, but with the evolution of Viaduct, we've started to build something we call Viaduct Components to power the next phase of SDUI at Airbnb. Viaduct Components are like React and Relay for the backend, but instead of vending DOM nodes in the browser, they vend JSON that can be consumed by our front-end frameworks. Components are built on top of the derived field provider framework I was just mentioning. They're similar to DFPs. They have a getFragment function that allows them to fetch data from the graph, But instead of a resolve function, they have a present function, allowing us to build a nested hierarchy of components, each with their own data needs. We can resolve this data in the same way as we resolve data for derived field providers, and then present the UI through the API. DFPs and components are very powerful, but today there are at least a few cases that they can't handle. Sometimes there's just something that's too custom and we need to break out of that abstraction. While we try to encourage folks to use service-back nodes, service-back connection, and derived field providers as their primary means for connecting data to the graph and transforming it, we have more advanced Viaduct constructs, type resolvers, custom implementations that ensures folks are never stuck and gives us data for how we might want to make certain use cases simpler in the future. So all of what I've showed so far is in production today, and we've been seeing lots of positive results. But Viaduct is still a relatively young platform, and we have lots of work we still want to do. With our consolidated schema and the fact we also enable people to write code outside of the typical service sandbox, we continue to work on improving our ability to host many tenants in one system. We're investing in ways to manage the ever-growing schema, modularize the code engineers write to make it possible for lots of engineers to work in the same code base, and are exploring ways to deploy the schema separately from the code, allowing for more frequent schema deploys to unblock development of new features quicker. Along those same lines, we're continuing to invest deeply in observability and resiliency of the Viaduct platform. For instance, we built an alerting framework that integrates with the ownership data in the consolidated schema to ensure we're paging the right teams when things go wrong, rather than solely relying on the Viaduct central team. And we're investigating ways to monitor resource usage, not just for the service, but at the GraphQL operation and even derived field provider level. Ultimately, as Viaduct continues to mature, we want engineers to think about Viaduct as a serverless system. They build their schema, configure the data dependencies, and write business logic in our opinionated framework, leveraging the building blocks we provide, and we host their data and their code for them in a Lambda-like architecture. If we succeed in this endeavor, we believe that we can amortize the service maintenance cost, reducing a significant amount of burden on product engineers, while still giving them the autonomy they desire when they build and run their own service, such as independent deployments of the code that they own and deep observability over the variables of the system that they can control. True serverless Viaduct is a ways off, but we're really excited by this direction. So I want to leave you with what we consider the 3 pillars of the data-oriented service mesh and what sets it apart from the traditional way of thinking about a microservice architecture. Data-oriented service meshes allow us to think and organize our systems in terms of data, not in terms of service boundaries and bespoke APIs. This opens up unique opportunities that makes data easier to access and simpler to consume and manipulate. The derived field providers I talked about earlier are very good examples of this. Business logic is now powered by the graph rather than a string of imperative service calls. The schema is the source of truth for the data-oriented service mesh. By designing the mesh schema first, we ensure we're focusing on the data and the connection between the data first and the services later. And finally, node-based data loading and designing the graph around nodes and edges, and building the primitives that allow your service graph to conform to that model are critical for bringing together services into a unified graph. This is what enables the deep connectivity that we desire in our consolidated schema. Thank you very much for joining me today. We're excited about how far this project has come and are looking forward to sharing more about Viaduct in the future. Thank you.
A data-oriented service mesh is defined by the properties of thinking about data, not service boundaries, the schema being the source of truth, and node-based data loading as the approach, which, man, there's a lot to unpack in that talk.
Yep.
Wow.
Yep. My mind is, I'm amazed. This is kind of what I meant by one of those things of like, taking kind of GraphQL problems by the horns and tackling them, right? And meeting kind of like where the Facebook monorepo reality is unfortunately not where is only a place where some companies are. It's not where other organizations can afford to be. And so having these, it is really important to have solutions that will allow for the same problem of this kind of data access and unified data to be solved in a microservices world, right? And this is a solid attempt that is kind of happening. There are 2 things that I absolutely loved about this talk, right? The first is that visualizing Viaduct as a 3D architecture diagram.
Yeah, absolutely.
That's an idea. That is an idea that I'm going to go and use for many things, right? I'm going to go take that idea for now I have a solution to, I can't draw the right Hasura architecture diagram because it's kind of between all of your services. So it's helping with the serverless functions, but it's also doing the data stuff. It's also doing the caching. It's this weird thing. And now the solution is 3D.
Well, even in a virtual event, I still write notes on paper, right? And literally the top note on my thing here says, I'm glad I'm not the only one whose keynote food doesn't allow 3D architecture diagrams. Like that has an exclamation point next to it here at the top, because you're totally right. Like, I think, in the abstract, Adam talked about sort of their transition from Ruby on Rails monolith to traditional SOA, to this sort of emergent new property of service-oriented GraphQL or the data-oriented service mesh. And it's that 3D component, I think, is interesting because it is taking what was sort of a very traditional ERD style thing, and it's extrapolating another layer of access on top of it. And
it's almost like this weird tangential feeling that I got, which is like things are becoming so complex that the tools that we use to communicate that complexity with each other need to change as well. And so much about the adoption of technologies depends on your ability to communicate and visualize it, right? And this 3D thing has gotten me all excited because I'm like, I had not thought about this dimension to communicate ideas. So that is exciting thing number one. But exciting thing number two was that I think it was super exciting because the way that we think about GraphQL at Hasura is so similar to the approach at Viaduct, right? Where they talk about, for example, their schema being the source of truth. Now, their schema actually is not really the GraphQL schema. It's like the GraphQL schema, but annotated with a lot of their own custom metadata, right? Where they define ownership and observability and derived fields, right? And so it uses SDL, but it is actually their own metadata. And they've created their own metadata framework to describe, and that is the source of truth of their data mesh, right? And that's exactly what Hasura's approach is as well. Oftentimes when from a point of like barrier to entry and the easiest way of thinking about what Hasura does, it's easiest to think about Hasura as like, it's taking your data models and exposing them as a GraphQL API, which is true, which is what it does. But actually the heart of it, and when you're using the Hasura UI and stuff like that, is actually the metadata. And you're using the metadata as that source of truth that you're actually constructing, and you're connecting that metadata to data sources. The idea of using the SDL to do that is also very interesting. There are pros and cons there, and so it'll be very interesting to learn from Viaduct in how they've solved those cons of being restricted to SDL as a metadata language, and not opting out into kind of something else they own, like full JSON or full YAML or something, which is the approach that we took. But otherwise, that idea, right? And I love the other articulation, which is that moving from a service-oriented mesh to a data mesh. So that's kind of what we were talking about when we were talking about the federation stuff as well, right? Which is that we have this, you can think about database federation, or you can think about API unification, right? And they're both different. They're both kinds of federation, right? But they're different. Like one results in a kind of federation that is kind of feels very thin, right? Because it's not taking away too many problems. It's a backend for front end kind of thing, right? You're just like putting together a bunch of APIs. It's very useful, but it's too thin to add real business value, right, for everything. So, and database federation is because that federation needs to have, like you need to have that data is customized or transformed or owned by policy, right? And that middle layer, right, is the exciting layer, right? The middle layer, being able to automate stuff at the middle layer, that is tremendously exciting, right? Or being able to say, here is the way that you can connect to data sources, derive it, here's how you can derive it, here's how you can attach policies to it, and make that declarative. So that whenever we make things declarative, it becomes easier to automate, right? So you make something declarative, yeah, you make things declarative, data fetching is taken care of, caching is taken care of, right? The whatever the ownership policy authorization is taken care of. And this was amazing. I'm super excited. I feel really bad that Adam is not here to answer the 1 million questions that I'm sure everybody has. That I have a million myself.
And I was just going to say the million that you and I have for him, let alone anyone else.
Exactly.
Perhaps it's a strange. You talked about how we visualize things is how technology is adopted. It's also how we tell stories. And one of the things Adam included as part of his story that resonated very strongly with me, it's related to what you just said, is you talk about the schema as the source of truth, but he also described it as the schema is the soul of the system. And in part because of my background, when I think of source of truth, it becomes very rigid and confining and limiting. Whereas instead, what they're saying is the schema becomes the rich tapestry from which a breadth of apps can be built and full pages can be rendered. But it still remains authoritative, right? And that sort of mix of authoritative, declarative, but flexible is where I would love to spend an amount of time bothering him about the developer experience to see where the edge cases are there, what the boundaries of that assertion are, because it's an interesting approach.
Yeah. Especially, I think, like often when we're talking about GraphQL, we always stress on the queries, right? We always talk about the queries and the reads, and so this makes sense. And one of the things that I wanted to hear more of is like how do they think about mutations in this, right? Because mutations are again the tricky thing. It's like what is the spec for mutations, right? How is that being handled? And that's one thing that for example, is it completely outside Viaduct? Is it like outside Viaduct? Is it a different system altogether? And Viaduct is only for reads. I'm not sure if I missed it, or I'm not sure if I didn't see it. I think it wasn't there, but yeah, that's for example an edge case of like how do you handle mutations that hit multiple services? What's the spec there, right?
Right.
Because that's kind of why. That's kind of the difference between the data mesh and the service mesh, right? In the service mesh, the reason why you have procedures, right? And I take a very database view of this, right? Which is that every SaaS service has a bijection with what a database is, right? It's like any SaaS service is essentially just like a database, but a database with stored procedures. That's what a SaaS API is, right? Salesforce is essentially a database with stored procs. Stripe is a database with stored procs. The stored proc is what lets you do the transaction, right? And then you get models that you can fetch and read and write, right? The difference between thinking in terms of like the data thing and the service thing is that stored proc thing. The service mesh makes you think of everything as stored procedures only. And the data mesh makes you think of everything as data only. But the data comes from a stored proc, right? The data is not necessarily coming from persistent model, it's coming from a stored procedure. That's the model, that's the mental model. Whether it's literally a stored procedure or not doesn't matter, right? So it's very interesting to, and the pieces, the piece with the most amount of tension between these two model of thinking is like writes and mutations, right? That's the biggest piece, right? Which is like writes and mutations are easier in the service-oriented way of thinking about things, slightly harder to think about in the stored proc way of thinking. I mean, not necessarily, but a little bit.
And just to make the talk even more compelling, Adam just happened to mention in chat that Viaduct does indeed do mutations as well. So yeah, I mean, it's exciting.
But Adam's here.
Adam, again, thank you so much. All right, with that said, it's actually time. Thank you always, Tanmay, I appreciate it.